Okay, this question is about light. There's a diffraction grating. You've got some wavelengths of different light here, and it says that both hydrogen and deuterium have red lines that are very close to each other and violet lines that are very close to each other as well. And down here it says that the deuterium and hydrogen red lines can just be resolved in the second order spectrum of diffraction grating. So first of all, we've got our order, which is 2. The deuterium and hydrogen red lines can just be resolved. So we're talking about the red lines. These two wavelengths can just be resolved. So we can take one of them as our wavelength, our initial wavelength, 656 times 0.288 times 10 to the minus 9. And then the change in wavelength is the difference between the two of them, which is 0.181 times 10 to the minus 9. Both those are in meters. And we're trying to find the grating spacing. So using we know that it's about resolution. We've got the information telling us it's been just resolved, so we can use our data booklet, and we can find our resolution equation, which gives us lambda over delta lambda equals mn, and n here is the number of lines that are being illuminated, so the total number of lines. So we've got lambda over m delta lambda equals the number of lines being illuminated, and that, if you put your numbers in there, that ends up giving you a number of lines that have been illuminated as 1813 lines. Now, that's not the final answer because we're trying to find the grating spacing, which is the distance between lines. So this is the number of lines in 3.5 millimeters. We want to find out how many millimeters is in one line. So we need to do 3.5 times 10 to the minus 3 divided by 1813, and that gives us 1.9 times 10 to the minus 6 meters, which is about that. Now remember, with a show question, you've got to show that the grating spacing, you should always give your answer to more significant figures here so they know that you've not just copied the answer from here. So we're giving 1.9 times 10 to the minus 6, which is approximately equal to 2 times 10 to the minus 6. Okay, the next part of this question is about interference. So we've got the first order of the red light in the hydrogen spectrum, so the first peak from the central maximum, and the second order line of the violet light in the hydrogen spectrum. So we're trying to find the angular difference from the central maximum to the hydrogen, from the central maximum to the red light in the hydrogen spectrum, the first order, and then the difference between that and from the central maximum to the second order of the violet light in the hydrogen spectrum. So I'm going to divide my page into two here, and I'm going to say the first order of the red in the hydrogen, and here I'm going to have the second order of the violet in the hydrogen. Okay, so now we know we're talking about interference. We know that the angle for a diffraction grating is given by this equation here, n lambda equals d sine theta. So here we've got n lambda equals d sine theta. So theta is inverse sine of n lambda over d. Now here n is 1 because it's the first order, so we can just get rid of the n. On this side we've got n lambda equals d sine theta. This time n is 2, so inverse sine of 2 lambda over d gives you theta. Okay, so now we're trying to find the difference between these two thetas. Let's call that theta red and that theta violet. We've got to find the difference between these two. Now we know the d, we've just worked it out in our previous question. The d was 1.9 times 10 to the minus 6. Now you can use the 2 from the previous question if you didn't, the 2 times 10 to the minus 6 if you didn't managed to work that out. So d equals 1.9 times 10 to the minus 6. For either of them, you still get the marks if you use 2.0 times 10 to the minus 6. There's a range for the answers in the mark scheme. And now we've got to work out what the wavelength is. The wavelength for the first order in the red spectrum of hydrogen, the wavelength red spectrum hydrogen, 656.288 nanometers. And the wavelength on this side is the violet in the hydrogen. Violet in hydrogen is 410.180. And so let's put that times 10 to the minus 9 as well. And so now we can plug that into the values here, and we get a theta red of 20.2 degrees, or if your calculator's in radians, 0.35 radians. And we get a theta violet of 25.6 degrees, or if your calculator's in radians, 0.45 radians. And so the difference, it says calculate the angle between those two. So the angle between those two is going to be 5.4. So the change in the angle is 5.4 degrees, or 0.10 radians.